Yeah, thank you. Yeah, I got some. Thank you, baby. How's it going, Eric and Kevin?
Hello.
Hello. We're a little early. I wanted to make sure I signed in and got everything working. So, but you're welcome to ask questions if you have any. Ooh.
This wasn't an optional lecture night, right? We're just a little early.
Yeah, that's correct. Just a little early. Man, evidently, every one of these notebooks have opened up from every class since I got my iPad is still loaded on here. I'm just realizing it now. Ooh, that's a lot. Still going. My cat's in the next room going crazy. And this looks like it. Yeah, all the way back from June. Woo. Let's see if it actually works. I'm going to try the share screen. It's again telling me I need to download something. I love that. Now let's see if it works. Yes, it is working. All right, so that's all working. So is Eric or Kevin or Esther, do you have any questions? I'm doing fine, Kevin. I'm still working on the remake of the midterm practice. Decided I was going to make one for each chapter, or actually two for each chapter, and it's taking a really long time. So it's going to be a little while, but I'm going to give y'all another chance to take another poke at the midterm. The cat's going crazy in the next room. Oh yeah, I forgot. I got a new background. Dog wants to teach you to brush your teeth. Oh, by the way, I'll share this with you guys. These people do some good physics stuff. Sometimes they're over the top with some corny crap, but still, uh, he does some really good stuff. Yeah, the second midterm is optional, but the way it's set up is I'm going to give you the higher of the two scores. So if you do worse on the second attempt, you're still going to get your score won't change. So yeah, that's called Veritasium. I just put up a YouTube link to it, and it's pretty good. I actually just found one in electricity that I shared to my 220, or excuse me, my 242 students. It was really, really good. but it's got fast Fourier transforms. I'm looking at it right now. Fast Fourier transform. How dangerous is a penny drop from the skyscraper? A cool one. This is the first time I ever saw it. Was actually him on campus explaining what happens when you drop an actual spring. That's kind of cool. Let's see if I can do that. Yeah, I think this is the first one. 10 years ago, this was posted. So yeah, I might check this one out. I think I like it. I sent that just to Esther last night. Well, it's supposed to go to everybody. Man. So first off, I'll send this one. Sorry, I just sent it to you, Esther. Was because I got the first one, but I sent everybody the actual more direct one. Let me go back now and get the. Oh, that's not right. You got another person in. Come on in, Joseph. So Adrian's here. Yo, Adrian. Now I got Joseph, Adrian, all sorts of people coming in. It's not time to start yet. It's about a minute from it, but you are welcome to ask me questions while we wait.
Yeah, I just gotta put my last name. My last name is Joseph Simon. I just gotta put my last name. I'm sorry.
No problem. So we got a Joseph, two different Josephs. Gotcha. I just wanted to make sure I was afraid I just let the same Joseph in twice by accident. So
Yeah, it's very confusing. I was telling somebody in the class that I'm just gonna call myself Simon now since it's two Josephs. I'm gonna call myself by my last name. It's two Josephs.
it doesn't help me because I'm so bad with names. The only thing that's really helped me is I noticed some of my students went and put their photo with their Canvas account. So like when I'm in there and I'm grading, then I can actually look at their Canvas grade and it will show their name and have a picture of them next to it. And I'm like, oh, okay, so that's who that is.
Yeah, yeah, that makes sense. Yeah.
I had someone that contacted me about a month or more ago about they actually had a death in the family. And I thought it was person A, but it turned out to be person B. And I had no idea until like the other day when the picture popped up. I'm like, oh, okay. I didn't know that person. I thought it was the other person.
Yeah.
So that helps a lot.
Yeah. All right. Cool.
I actually used to make a Facebook page and then invite all my students, but I felt kind of creepy because it was like, I had a Facebook page and then I had all of my students and all the stuff they post would come up there and I'm like, oh, I don't think my students want me looking at all their crap. And, so I just stopped making that altogether. It's okay for them to follow me, but they can't like follow me without me being able to follow them. And that's not cool. But it was nice for a while because I could learn names pretty quickly. All right, so time for class to begin. So last time we met. I'm going to pull up my notes to refresh my memory, but if I remember correctly, we actually did some moments of inertia, calculating some stuff that, sort of the more calculus based stuff that you don't normally get to do. I did a cylinder rolling down an inclined plane, and I calculate what the acceleration of that was. And I'd made that mistake about a negative sign or a positive sign or something along those lines. But then I corrected it. Then I had a student ask me at the end of class about a specific problem. So if you look at the video at the end, you'll see me working out a problem. And that's actually on the last page of the notes from 11/02/22. So yeah, we did find the acceleration was about 2/3 g sine theta for that one. Yeah, and before that I did a cylinder and calculated the moment of inertia for that cylinder. And before that I did for a rod rotating about the center, and then for a rod rotated about the end. And I gave you an introduction to torque, so you had some idea what torque was. So does anybody have any questions about that stuff that we covered last time? Okay, and I was telling the people that got here early, so I am giving everybody a chance to do a redo on the midterm, but it is optional. But it's also the fact that whichever scores the highest, this one or the last one, that's the one that counts. And I'm also not taking away the extra niceness that I gave you, which is that if you do better on the final than you did in the midterm, then I will replace your midterm grade with your final exam grade. So all that still applies. I just want you to have another chance to do better and make yourself feel better about your ability to do it. It's really self-defeating. Sometimes when you get hit by a test and you don't do very well, especially if you felt like you were doing pretty good in the class and then it hits you. So part of the problem is, like I said, it's hard to gauge exactly how much you lean on a resource until you have to go without that resource. And that's what my midterm is. That's why I always have at least 2 tests in a semester that are a significant fraction of the grade, so that first one, everybody can get an idea. Oh, well, okay. So yeah, I was evidently leaning on it too much because I was doing, all 95s and 100s on my test online, where I'm allowed notes and notebooks and textbooks and Google and all that good stuff. And then boom, I get hit with a 42 or 26 or something on the midterm. So that's why I always do that. I just want to make sure you guys get a chance to see what it's like. And then if it's bad enough, like it was this time, not necessarily with your class, there was one section that had really bad time, and I decided to do a retest for them. And then since I was doing it for them, I decided to do it for everybody, which is nice. I like doing that for people, for my students, but it's a lot of work. So now it's going to take me a little while to make up all those tests. And plus a lot of them were concerned that I'd made up a practice midterm that was geared towards the latest chapters, but the actual midterm was sort of equally weighted throughout the chapters. So that presented a whole nother problem that they didn't like about the midterm. So I decided to just probably make 2 quizzes for every chapter, or maybe I'll make one with a concept question and one with one concept question and one problem for each chapter. So every time you take it, you get one concept and one problem, one concept, one problem. And then I'll do another one for chapter 2 and another one for chapter 3 and so on and so forth. So that's what I'm decided on, but I'll put them in the week modules, because like week 1 we did chapter 1. Actually, I think week 1 we did chapter 1, and then week 2 we did like 2 and 3. So it'll be stuff like that. Anybody have any questions about that?
Are you using the lockdown browser for that?
Yes, for the midterm this time, it's going to be lockdown and respondus monitor. So not only are you having the lockdown browser, but you're going to have a camera. If you don't have a camera, then you can either go to school and find the one that does have a camera, go to the testing center and have it done there, or whatever you want. Just let me know. Okay. Basically, I just have to have someone, either me or the respondus people and me, or the testing center people, making sure you don't have access to anything. So that's why you got to be on camera and all that good stuff. But again, you're not required to have a camera. That's why 1, the test is optional, and 2, if you don't have a camera, you can do it some other way by, like I said, the testing center or something, or you can just get a camera. It looks like just about all new laptops have them, and desktops seem to have them as well. And then I found cameras for pretty cheap, like 10, 15 bucks. But you know, if you're having a hard time, you ain't got a job, 15 bucks is still a lot of money. So, all right, well, I guess I'll get started since it appears no one has any questions. When I do finally post that test and the practice test, I'll send you an email. So it might be something where I might not get to it till maybe I release the actual test over Thanksgiving break, and then that'll be fine. You can have all the Thanksgiving break, and maybe I'll give you 1 or 2 days after that to finish the test, in case, you know, you went somewhere cool and had fun for Thanksgiving. I don't want to spoil that for you. So let's go ahead and get started. I got a couple of very specific problems I want to work with you and see if you can make sense of them. And I'm going to do one that's really quite complex, and then I'm going to do a second one that's quite a bit less complex. But in that one, I'm wanting you guys to do it along with me. So I want you to pay close attention to how I do the first one, and then we're going to use those sort of same techniques to do the second one. So first off, I'm going to go ahead and share screen, because otherwise I'm going to forget and just y'all be talking to the top of my head again. Not like you've never done that before, huh? Look, Mr. Younger's liver spots on his head. All right, so we now have this. So what's the problem I'm going to work? Well, what I'm going to work is basically an Atwood machine type of problem. So I am going to say we have a circle, and that's actually a cylinder, by the way. And another circle, that's actually a cylinder, by the way. And what it is this inner circle has a radius little r, and this outer circle has a radius big R, and big R is corresponding to a cylindrical disc of mass big M, and little r is corresponding to another cylindrical disc that's glued to the first one, and it has a mass little m. And we'll say something like big M equals 5.00 kilograms, and R is equal to 10.0 centimeters, and little m is equal to 1.00 kilograms, and little r is equal to, let's say, 7.00 centimeters. Okay. And what I'm going to do is I'm going to hang a mass from this one, and that's going to be mass M1. And then I'm going to hang another mass from this one, and this is going to be M2. And I'm going to say M1 is equal to 15.0 kilograms, and M2 is equal to 30.0 kilograms. Okay. Now what we're assuming is this rope is actually wrapped around the pulley, so it's going to pull and not run out of rope. And by the design, it looks like M2 is considerably heavier than M1, and they're both actually considerably heavier than the actual pulleys. So we expect M2 to sort of win the battle, if you will. M2 is going to accelerate downward, and what we want to calculate is what is the acceleration A2, what is the acceleration A1, and you might not realize, but yeah, you're going to have different accelerations because they have different radii. And then what is the angular acceleration alpha? And then what is the tension on the left-hand side? Because it turns out you're going to have 2 different tensions, and the tension on the right-hand side. Okay, that's really what we're shooting at here. I'm going to do it all in symbols so we can have something that we can compare. We can look how it changes if you allow certain changes and stuff like that. It's a much better way to solve problems in physics if you can do it. Now, if you're doing this, you probably throw the numbers in immediately, and that's just fine. I'm just saying that if you can do it symbolically, you'll have an answer that works for all of these problems, no matter what the masses are I give you. And even you can consider the cases where the pulley has no mass and all that good stuff. We could also, by the way, easily add a friction force to this pulley, and that would allow yet another thing we could solve for, or another variable we could put in and make it more realistic. I'm going to assume with this one that it has no friction. So my assumptions are no friction, no stretching, so the springs don't stretch, no slack, so the strings don't get loose, and no sliding. So that means the string, if the string on the right, that's a D there, if the string on the right moves 1 inch, that means the circumference of the big pulley is going to move 1 inch. So if you made a mark, for instance, on the pulley where the string just leaves the pulley, if the string moves 1 inch, then that dot will move through an arc length of 1 inch. Okay, so that's what I mean by no sliding. It's just it's going to force any inch long movement of the right string to make an inch long arc length on the big pulley, and any say inch long movement on the left string is going to make the inner pulley, the smaller one, move through an arc length of 1 inch. Now here's the kicker. If the inner pulley turns to an angle 30 degrees, since they're glued together, the outer pulley is also going to move to an angle of 30 degrees. That's why I didn't have to subscript the alpha. The alpha is the number of radians per second every second, which doesn't immediately translate to you understanding that. But if you were to integrate that, realizing that alpha is actually the d omega over dt, which is equal to the r times the omega, okay, then, or r times the d omega over dt, excuse me. Yeah, the alpha is equal to d v dt, which equals r times d omega dt. And if you integrate that again, then you see that the s, the arc length moved, equals the r times the actual theta is moved through. So all of that just tells you when you have sliding without slipping, or rolling without slipping, or no sliding like this is, that all just means that the equation is like s equals r times theta. That holds. It also means that v equals r omega holds, and it also means that a equals r times alpha holds. Okay, in this case, we've got two different a's though, and I'll get to that in a second. So the first thing I want to do is I'm going to go on the assumption, because M2 is so much larger than M1 and so much larger than the mass of the pulley, I'm going to go on the assumption that this setup is going to have the mass M2 go in the downward direction. And I don't want to deal with very many negatives, so I'm going to call M2 going in the downward direction as the positive direction. So solution, three-body diagram for M2. Okay. So what I'm going to do is I'm going to draw the mass M2, or I'm just going to randomly erase a spot because my iPad's going to change it. That's going to be M2. What I'm seeing now is the positive X direction is down. So I'm doing like that. And in fact, that vector that points that way will in fact be the weight, which is given by M2 times G. Now, if you were to talk to M2 would say, well, I was falling at 9.8 meters per second, but something, that rope, that string that's hung on my back is evidently slowing me down, which is, I'm thankful for, because I might have hurt myself when I hit the ground, but now it's slowed me down so I don't quite accelerate as much. So that tells you, oh, the tension is pulling up, and I'll indicate that's in the negative direction by making it black. And that's going to be what I call T sub big R, or T sub R for right, or you could treat it as big R for the fact that it's on the big radius. Okay. So that's our free body diagram. And of course, the reason you draw free body diagrams is so that you can write a F equals MA. So what does, for this particular one, what is the summation of the forces in the X direction equals mass 2 times acceleration 2. What does that equation look like from this? So you guys try to write out your equation. using, you know, one of them's going to be positive, the other one's going to be negative. Go ahead and write that out and see if you get the same thing I do. Okay, I'm going to write my answer now. Hopefully y'all have already got yours. Okay, that's going to be equation 1. So hopefully y'all got that. Now we're going to do a free body diagram for M1. Okay, now the way you do these problems to make your life less difficult is once you've chosen a positive direction, everything consistent with that being moving in a positive direction should also be positive. So for instance, if M2 is going down, what's M1 doing? Exactly. So that means the x-axis for M1 is pointing up. So I'm going to draw M1 right here. And then I'm going to say, okay, well, the force acting upward, I've evidently called that blue. So that's going to be the tension on the left-hand side because I called that TL earlier. And of course, the negative force in this case is M1G. So now I want a summation of the forces in the x direction equals M1 times acceleration 1. So what is that equation? See if you guys can write that out, and I'll write mine out and see if we get the same thing. I'm going to go ahead and take up some of the space down here, and I'm going to write this as and that's going to be called equation 2. Hopefully everybody got that. Everybody get that? Anybody have any questions on how I got that or need any help getting that?
My question is, why is the tension left still going up?
Okay,
On the
so exactly. So that's a really good question. That's a very typical question too. So what you want to think of when you're thinking of this is sort of like I did when I drew M2. I said, you know, if you were like in a box that's represented by M2 and you were hanging from a rope that goes over up some pulley off of a skyscraper, you would realize that you're falling downward, but luckily that rope is slowing you down a little bit, right? You can see that you're going, and it's kind of scary because you might get going fast enough that you die. But while you're falling, you realize, well, at least it's slowing me down a little bit, so I got a better chance to live. So that tells you unequivocally that the force of gravity, which you already knew, was pulling you down, and therefore the tension must be pulling up on you. That's why the TR is up in the first diagram. Now, if you think about the second one, if you're just happen to be standing on this box trying to weight it down and all of a sudden it took off upward, you're stuck in an elevator going up, right? So to you, you're like, oh crap, I thought my weight and the weight of this stupid box was enough to keep me on the ground, but evidently this dang pulley has something on the other end of it because the rope going to it is yanking us up. So in that case, I think you see that, oh, so from the inside the box of M1, clearly the tension on the left is pulling up on it. Does that make sense?
Yep.
Okay. Now watch how it's really, see, this is where it's going to get really crazy because I'm just getting ready to switch now. I'm going to do the free body diagram for the pulley, and it's all going to be different. So just be prepared. So free body diagram for the pulley. So here's our free body diagram for the pulley. I'm going to draw a big circle. And then I'm going to draw a little circle. And what I'm going to do is realize, okay, according to the pulley now, notice I'm talking about what the pulley thinks. The pulley thinks, hey, I'd be sitting here fine if these two ropes were pulling the same amount. But in fact, that's not what's happening. there's a rope on the right-hand side that's pulling down, and that's making me rotate clockwise, as seen by us. So what I'm going to do is I'm going to say, okay, here's the tension. In fact, this is the tension TR. Okay, and I made that blue because if the actual cylinder, the pulley that's made out of a cylinder, if that's actually pulling down on the right-hand side, that's the same thing as M2 going down, and therefore it needs to be positive. So this torque needs to be a positive torque, or I'm going to get jacked up stuff. Now, according to the pulley, it says, yeah, that stupid rope on the right is spinning me, but luckily the rope on the left is tending to slow me down. So now I'm going to draw yet another force, and this force acts this way, and that force is going to be TL. But notice if you look at TL with the free body diagram for M2, or excuse me, with the free body diagram for M1, you see that the TLs sort of cancel each other out. They're going opposite directions. That's what you expect to happen on your free body diagrams. If it don't do that, you've screwed up. And similarly, the TR points down on the pulley, but it points up on mass M2. So they're canceling out as well. So that's the way it's supposed to look. Now, the Newton's second law version for a torque is, in fact, the summation, not of the forces, but the summation of the torques is equal to I times alpha, where I is your moment of inertia. And remember, torque is equal to R cross F. That's one way of looking at it. But you could also say it's the component of R perpendicular to F, or you could also say it's R times the component of F perpendicular to it, or you could say it's R times F times the sine of the angle between them when they're tail to tail. Notice I made that into just a scalar by not putting the vector symbol. So those last three are all equal to each other, but they're not technically the same thing as the top one. So in order to get a torque, you need a force times a lever arm. And if they happen to be at 90-degree angles, as they clearly are in this case, notice from here to here, that's the lever arm. And notice from here to here, that's also the lever arm. And notice that they're actually perpendicular to each other. So R perpendicular times F is the same thing as R times F perpendicular, and it's the same thing as R times F times the sine of 90. So again, to be consistent with my units, I mean, with my signs, M2 going down was positive. That meant M1 going up was positive, and that means this pulley rotating clockwise is positive. So I'm going to take a torque that causes clockwise rotation and make that positive, and that means my equation should be big R times TR minus little r times TL is equal to, now the moment of inertia for a cylinder is 1/2 mr squared. So I'm going to put a 1/2 because that's going to be common to both of them. But for the small pulley, it's going to be little m times little r squared. And for the big pulley, it's going to be big M times big R squared, and then times alpha. And because I wrote that so small, I wanted to make sure you guys can see it. Everybody see what I wrote there? Let me clean it up a little bit while I'm at this scale. Okay. Okay, this is going to be equation 3. Does that make sense to everyone? Everybody understands where that came from and everything, right? All right, now it looks like we have the unknowns are A1, A2, TR, TL, that's 4 so far, and alpha, that's 5. I've only got 3 equations. Good news is this. We also know, since this rope is not sliding, we also know that A1 is going to be equal to big R times alpha. And that'll be equation 4, say. And we also know, again, because there's no sliding of the rope, we know that A2, ooh, I got that backwards. Let me let this person in. I can. Okay, I got that backwards, so let me fix this right quick. Okay, so remember A2 is the one that's corresponding to the M2. So I dumbly wrote A1 next to it because, you know, I'm a goober. So anyways, now A1 is also going to be equal to, in this case, lowercase r times alpha. But like we said, if cylinder 1 moves through 30 degrees, the smaller cylinder, then cylinder 2, the bigger cylinder, is going to move through 30 degrees. So those two alphas are exactly the same. So now I've got 5 unknowns and 5 equations. Life is golden. Okay. Doesn't necessarily seem like an easy thing to solve, but it actually is pretty straightforward. So the first thing I'm going to do is to solve this. I'm first going to solve for TR in number 1. Whoa. So let's call this equation 1 star because it's 1, but just 1 manipulated. That's going to be TR is equal to M2 times parentheses G minus A2. And equation 2 star, actually that was 2 star. Let me put that 2 on there. Notice I just magically changed that 1 into a 2. Okay. Since I was dealing with math 2, I should have known it was equation 2, but I did not because, again, I'm a goober. So equation 1 star is going to be me solving equation 1. Dang it. I did have it right, didn't I? Yeah, 1 was equation 2. Okay. And when I do want to erase, it won't erase. It looks like evidently I didn't label that equation for M2. I did label that 1 star. So let me, get rid of the rest of this. Okay, got that. Now, so this evidently that was right to call it 1 star. So I'm going to call it 1 star again. Sorry about that, folks. I thought I made a mistake, but I didn't. Therefore, I made a mistake. Now, 2 star, I'm going to solve 2 for TL. And that's new relationship, even though it's the same relationship, but just solved for a different variable. It's going to be called 2 star. So that's TL. And that's going to be equal to M1 times A1 minus, plus G. So notice I've got M2 times, because the TR was negative on the left. So if I pulled it to the right, it become positive. That meant the M2G was going to be positive, but the M2A would be negative. So that's why I've got those 2 versions. Now I'm going to plug those into equation 3. Okay, so when I do that, equation 3 is going to become big R. Now TR we said was M2 times G minus A2. And then TL, which is the next part of equation 3, we have a little r and then a TL. And that TL we said was M1 times A1 plus G. So that's the left-hand side. The right-hand side is going to be 1/2 M. Sorry, I got to write this so small. but that's that, okay? And we can call this equation 3 star. Actually, we'll call this equation 6. So we plug that in equation 3 and got this. Now, this might seem horrible because now we have A2, A1, and alpha. That's one equation with 3 unknowns, but we can express A1 in terms of alpha. We can express A2 in terms of alpha. And then when we do so, the equation will only have alpha in it. That's the only unknown, and we can solve for it. So now I'm going to say, solve for A2 and 5 for A1 and plug them in. So now when I do all that, you can see, let's try to make this a little less confusing. So I'm going to write this right here to try to keep track of what's what and what's separate. So I'm just going to put that right there and that right there. Now I can write out this equation again. I'm going to have, going back to red, I'm going to have R times M2 G minus R M2. Now A2, according to equation 4, is R times alpha. So I'm going to say this becomes R squared and times alpha. And now I also have minus R.
Should that second M2 be an M1?
Probably, I would. You talking about in equation 6, or are you talking about in the one I just wrote?
The one you just wrote.
Okay, no, it should be M2 because I distributed this this term right here. I distributed that factor in this term. So I did R M2G, that's the first one, and then R M2A2. Does that make sense?
Oh, okay, yeah, I see that. Thank you.
Okay, and I'm going to make it bigger so you guys can actually see it. So now I've got R times M2. That's what I already had up there. And the negatives out in front. And then I have A2 is R times alpha. So I'm going to make this R squared and call that alpha. And then I've got little r M1A. So little r M1. And now A1 is supposed to be R little r times alpha. So that's going to make this R little r squared times alpha. And then notice it's a minus in front of the M1, in front of the R M1, and then an A, and then the minus is going to hit the G as well. So I'm going to say minus R M1 G. That's the whole left-hand side. Does that make sense to everyone? So now I'm going to take the right-hand side and notice that was just 1/2 MR squared A. So I'm going to say 1/2 little m little r squared alpha plus 1/2 big M big R squared alpha. So you can fit it in that small space, but obviously we need to zoom in when we're doing it. That's the only way I can recover. So now what I want to do is get all the alphas on one side. So in doing that, I'm just going to see that I have an R M2G. That's going to stay here. And I have an R M1G with a negative in front of it. That's going to stay here. So the only thing they really have in common is the G. Is not much use in really factoring that out, but I'm going to do so anyways. So let's do this. We're going to say R. Actually, I don't want to do it that way. I want to do it in a different order. I want to do M2 R minus M1 little r times G. That's taking care of those two blue ones. That's going to be equal to, now notice this R squared M2 alpha is going to become positive on the other side. So I'll say M2 R squared alpha. And this R1 or R squared M1 alpha, that's going to be positive on the other side as well. Let's look back and make sure I didn't make any mistakes on that. Yeah, the A2 was negative and the A1 was negative. So yeah, that's right. So this is going to become plus M1 R squared alpha plus 1/2 M R squared alpha plus 1/2 big M R squared alpha. So literally we couldn't see that if it wasn't for us zooming it in. So I'm going to write it down on the next line and factor out, let's say, a common alpha. Next line, notice is quite a bit longer. So I'm now going to say I've got M2 big R minus M1 little r times G is equal to, now it looks like two terms have an M, have a big R squared and an alpha in it. That's the first and the last. So I'm going to make use of that, and I'm going to say M2 plus 1/2 big M times R squared. So that takes care of this guy and this guy. Now, what I also realize is M1 has a R, little r squared, so does little m. So I'm going to do the same thing with that. Notice there's still a factor that's here. I left that out on purpose. The alpha is going to be outside of this bracket. So I'm going to put this bracket here to remind us that's what's going on. So this is going to be plus parenthesis M1 for that second term plus 1/2 little m for that third term times little r squared. And now that means I've taken care of that term and that term. The only thing that's left, of course, is the alpha. So I'm going to go ahead and finish off this bracket and put alpha right there. The reason I did that is now I have the perfect way to solve for alpha. All I have to do is divide by that term in front. So what I have now is finally alpha is equal to M2R minus M1R. All that is going to be over. I really hated that line. That made me mad. There's going to be a G outside. Okay. Now the bottom's going to be M2 plus 1/2 big M times R squared plus M1 plus 1/2 little m times little r squared. So that's it. We've actually gotten the alpha. Now, if you look back at equation 4, that means A2 is just R times alpha. So if I multiply this by big R, then that'll give me A2. If I multiply it by little r, that'll give me A1. Okay, now I'm going to try to steal and put this on the next page. No. Anybody know how to get this to paste? This is going to be very helpful if I do. I do not see paste there.
You should be able to hold down the screen and then it will say paste.
Ah, there you go. Thank you. I was tapping, that wasn't working. Okay, there you go. Cool. So that's what I got for my alpha, right? I could go ahead and finish that box, of course, that might make it look a little better. So that's one of them. And that tells me that, of course, A2 is equal to big R times alpha. So that means A2 is equal to M2 big R minus M1 little r. All that over M2 plus 1/2 big M times R squared plus M1 plus 1/2 little m little r squared times big R G. Now, if you notice, that's a MR squared in the top because MR minus MR has units of MR times another R, that's MR squared. And then in the bottom, I've got MR squared as well. So yeah, that is actually giving me units of acceleration, even though it looks like it might be something different. So that's A2. And A1 is equal to little r times alpha. So A1 is going to be equal to M2 big R minus M1 little r over M2 plus 1/2 big R times R squared plus M1 plus 1/2 little m little r squared times, this case, it's going to be little r times G. So I've now gotten 3 of the unknowns. I will leave the rest to you, but all you have to do now is that TL was equal to, what do we say? TL was equal to M1 A plus G. So really what you got to do is take that M1, multiply it by the A1 that we have, and then take that M1, multiply it by the G, but get a common denominator. So I'll do that one for you just to show you. So TL is going to be equal to, I'm going to take this A1, I'm going to multiply it by M1. So I'm going to get M1, M2 R minus M1 squared R. And why not the heck? Yeah, I'll go ahead and put this big R, or excuse me, this little r inside of there. So the little r here. And all this is going to be M2 plus 1/2 big M times R squared plus M1 plus 1/2 little m times little r squared. And all I have left is a G over here. Now, what I could do, since I have that common factor of M1, I could pull that M1 out and stick it over here with the G. Then it would be a dimensionless thing on the left times M1G, and M1G clearly has the units that we want. Now, here's the problem. That's just the first term. So what I need to do now is get rid of that G that I just put there and just hold it for a second. And what I'm going to do is I'm going to put a little plus symbol. Whoa, or evidently I'm going to erase something. I'm going to put a little plus symbol right here. And now I'm going to take M1 and multiply it by G, which I already factored out G here. So the G is going to be outside of all this, just to remind us. I'll put this big bar here and I'll put the G out in front. That'll help us remember. But what I want to do is go ahead and get the same denominator as this fraction has. So all I'm doing is I'm taking the G and I'm putting an M1 up top and multiplying it by the denominator. So I'm going to get M2. Well, let's not do that color. I'm going to get M1, M2 plus 1/2 M1 big M R squared plus M1 squared plus 1/2 M1 big M, that all times little r squared. And all this will be over the exact same denominator I had, which is blah r squared plus blah little r squared. Now, ideally, some cancellations will happen in here, but you can see it's not going to be a whole lot. It's actually not going to do much good at all. But either way, we can still say TL. I'll try to write it further over to the left. So TL is going to be M1, M2 big R minus M1 squared little r. Actually, I'm going to go ahead and distribute everything so I can see M1, M2, little r, big R, minus M1 squared, little r squared, plus M1, M2, big R squared, plus 1/2 M1, big M, R squared, plus M1 squared, little r squared, plus 1/2 M1 big M, little r squared. All that's going to be over M2 plus 1/2 M big R squared plus M1 plus 1/2 little m little r squared times G. Now, do we get any cancellations? Well, I have an M1 and M2, and that's the little r times the big R, and then M1, M2, and that's the big R squared, so that doesn't work. So I'm going to say nothing there and nothing there. How about an M1 squared? Well, I've got an M1 squared negative with an R squared, and I've got an M1 squared positive with an R squared, so that actually does cancel out. Then I've got an M1 big M, R squared and that squared. So I can at least make some simplifications. So finally, my answer is going to be TL is equal to M1, M2, both have a common factor of R. So I can write this as M1. Actually, I don't want to write it that way as M1. I'm going to say M1 times R. So that takes care of that first term, but it's going to have a M2 that I'm going to make use of. Minus, or excuse me, plus. Oh, I left off the dummy. Actually, it's probably easier to just erase. I left off the M1, M2. So what I'm doing is, I remember that the tension from the Atwood machine, let me write it up here. The acceleration from the Atwood machine was M2 minus M1 over M2 plus M1 times G. And the tension from the Atwood machine was 2M1 over M2 plus M1 times M2G. So I'm trying to make it look like that, in other words. So if I take the M1, M2, I can say M1 times R. Let's just write it, say M1, and why am I doing blue again? Damn. Okay. That's the first term. So I want to say check. Plus M1, M2 big R squared. That's the third term, check. Plus 1/2 M1 M big R squared. That's the next term. Plus 1/2 M1 big M little r squared. All that divided by M2 plus 1/2 big M big R squared plus M1 plus 1/2 big M, or excuse me, that should be a little m. Little r squared, and all times G. So you can see I do have a common factor, say, of M1 that I can pull all of this out by and put the M1G over here. I can't do that with the M2 just because the M2's on there is only on the first two terms. But if I try to examine this acceleration A2, so let's look at A2 up top. That's the acceleration of the thing on the right. So that should, you know, in the same conditions as the original Atwood machine, which is M2 and M1. M2 is larger than M1. And the radius, of course, little r and big R are the same thing because it's just one pulley with one radius. But the little m and the big M are zero mass. So if I look at equation 2 and I let big R equal MR equal little r, then this R and R can be factored out of the numerator. And then that R squared in the bottom and the little r squared at the bottom can be canceled out as just a R squared as well. So now I have a R from M2 minus M1, and then I have an R from next to G. So that's R squared over R squared. They cancel out completely. And I'm left with M1 or M2 minus M1 in the numerator. And then the denominator is going to be M2 plus M1 in the denominator, and then times G. So I get exactly the same result A that I did for the original Atwood machine when I let R equal big R and little m equals big M equals 0. Similarly, you get the exact same thing if you do that with A1. And now let's look at the tension. If I actually considered the big M and the little m equal to 0, those last two terms in the numerator would be 0. And the RR would be R squared, and the R squared would be R squared. So that R squared can factor out of those first two terms. So I'd have M1, M2 plus M1, M2. That's literally 2 M1, M2, which you can see is the top of the tension up in the top right corner. Plus 0, all that times G, of course. And then in the bottom, all I'm going to have is M2 plus M1 because the big M and the little m are both 0 as well. And the R squared and the R squared cancels out with the R squared and R squared up top. So yes, this is exactly what we'd expect to get. And that gives us a great deal of confidence that we did it right, because you wouldn't expect it to get the same formula if we'd made an error. Now, it's not 100% guaranteed that it's right, but that passes a good test, okay? So if y'all want to, for extra credit, you can solve for TR. And you saw how I did that. Any questions on that? So if you look back through this process, what we did was we had a diagram, we had an idea. My idea was, hey, it looks like M2's much bigger than M1 and much bigger than little m and much bigger than big M. So I suspect M2 is going to fall. That being the case, I'm going to call that direction positive so I won't have a bunch of negatives floating around. So that made me make a free body diagram for M2 in which down was the positive direction. So if M2 goes down, that made me decide that M1 would be going up. So M1 going up must be a positive direction. So that's why I made the positive direction up for the second free body diagram. And then I just made the free body diagram, used F equals MA with the appropriate signs. And the same thing for the second one, use F equals MA with appropriate signs. And I got equations 1 and 2. And then I did a full free body diagram for the pulley. And that one, of course, has the equation, the summation of the torques is equal to I times alpha. Now, I's aren't vector quantities, so they just add. So I had a cylinder whose moment of inertia is 1/2 little m, little r squared, and a big cylinder whose moment of inertia was 1/2 big M times big R squared. So I just added those two, and that's what I got on the right-hand side of equation 3. What I did notice, though, is if M2 in fact falls downward and the rope doesn't slip or slide along the outer surface of the big pulley, then that means the big pulley turning clockwise should also be positive. That's why I made the big R and the TR both blue to show that that's going to be my positive torque. And then the black R and the lowercase r and the black TL, those are in the negative direction. So I got big R TR minus little r TL is equal to 1/2, like I said, the moment of inertia times alpha. Again, I use the fact that the rope wasn't sliding. So A1 is equal to R times alpha and A2 is equal to R times alpha. And all I had to do was solve equation 1 for TR, equation 2 for TL, and then I could plug those directly in equation 3. And that reduced that sort of made it worse. It gave me one equation that no longer had TR or TL, which I didn't want to know immediately anyways, but it introduced A1, A2, and alpha. So I had 3 unknowns, but I had a relationship that related A2 to alpha, and I had a relationship that related A1 to alpha. So I used that, and that made one big equation that literally had one unknown, and that one unknown was alpha. That's how I got equation 6. Well, that's how I took equation 6 and got what's below it and had nothing but alpha in it. That allowed me to solve for alpha. Once I had solved for alpha, then I could just multiply it by big R to get A1. I could multiply it by little r to get big R to get A2 and little r to get A1. And that was it. So I found A1 and A2. Then I could go back and use my expression for TL and my expression for TR to get what the tensions are. Of course, the hard part was getting a common denominator. It's not really hard, it's just a lot of algebraic work. But I did one of those for you. That should help you. So everybody see that way that I did that? That makes some sense. Anybody have any questions about that? Like I said, the big thing about this is keeping all those positive will keep you from having little missing signs. If you don't pay attention to that, you could get my free body diagram 1 calling down positive and my free body diagram 2 calling down positive. And then the relationship between A1 and A2 is A1 is equal to negative A2. That's just a pain in the butt, right? And then what are you going to do with alpha? Is alpha A1 or is alpha little r times A1, or is it negative little r times A1? Is it big R times A2, or is it negative big R times A2? So by keeping all that together and making it all consistent, you don't have that problem. Man, all that time I was writing with a page that was shrunk, so I was trying to fit all this junk in. I didn't realize, look at all the column I left to the right. Anyways, anybody have any questions on that? So remember, in the limit, I'll say limits of M equals big M equals 0 and R equals big R, then A1, I'll say A1 equals A2 went to M2 minus M1 over M2 plus M1, all that times G, which is exactly the Atwood machine, and TL equals TR went to 2M1 M2 over M2 plus M1 times G. So that's our pat on the back. Now, I didn't actually verify TR, but it's got to do that. So there's a goal for you when you solve for TR for extra credit. If you solve it for extra credit, it better do that in this limiting circumstance. If it doesn't, you got it wrong. All right. Now that I've sort of given you a nice sort of blueprint of how to solve this, what I want to do is see if you can solve one. So I'm going to draw the diagram. And here it is. So there's my pulley. It's a cylinder. Oh. I want that back. Okay. So a cylindrical pulley M equals 5.00 kilograms and R equals 10.0 centimeters. Okay. And then I'm going to have a mass M2 on this side, and M2 is going to have a mass of 30.0 kilograms. And M1 on the other side is going to have a mass of 15.0 kilograms. That's M1. So what I first want you to do is, well, the goal here is to say what is A1 equals A2 equals just plain A, because we don't have any different radii here. So we don't have to say they're different. So I want to know what that is. We do have a difference in tensions though, because the pulley is massive. So I want to know what TL is equal to. I want to know what TR is equal to. And I want to know what alpha is equal to. So that's the goal. So first off, I want you to draw a free body diagram. So you do this now for M2. So everybody go ahead and do that. Now that should be done already because it's not that hard of a drawing. You need a dot, you need a line pointing a particular direction with an X marking it and an arrow. So you can choose which direction is positive. And then you need a vector representing each of the forces acting on M2. Now that you have all that, write F equals MA for that free body diagram. I'm choosing down to be positive again, so this is going to be M2G. And this is going to be TR. And therefore, my equation is M2G minus TR is equal to M2A. And A1 equals A2 equals A because there's not going to be any sliding or slipping. If mass M2 goes down 1 inch, then mass M1 is going to go up 1 inch. If it goes down 1 inch in 1 second, then M1 is going to go up 1 inch in 1 second. So the average velocity of M1 is equal to the average velocity of M2. If it goes from 0 meters per second to half a meter per second in 1 second, M2 that is, then M1 is going to do the same thing. So A1 is equal to A2. That's how I'm actually making that conclusion. So this is going to be equation 1. Now do a free body diagram for M1. I'm going to make that one a little shorter so I can fit the equation from Newton's second law on the line right above the line I just used. All right, now that you have your free body diagram for M1, go ahead and write F equals MA. In other words, the summation of all the forces is equal to mass times acceleration for body for M1. So everybody get that equation of motion for free body M1? Anybody have any questions on how I got them or how I got those free body diagrams? Now we're going to do a free body diagram for the pulley. Okay. So you guys, again, I want you to draw a free body diagram. I got you started. You're going to draw a circle for the pulley. You need to show TR and TL, and they need to point in the correct directions. And one of them needs to be indicated as positive, and the other one needs to be indicated as negative, so that it's consistent with free body diagram for M2 and free body diagram for M1. All right, now that you have the free body diagram for the pulley, I want you to do the summation of the torques is equal to I times alpha. Remember, this is a cylinder, so you know what I is for a cylinder. But of course, one of the torques needs to be positive and one of the torques needs to be negative. So hopefully you got that right. So go ahead and write that down. I'm going to go ahead and start drawing my free body diagram, and then I'll draw my equation. That's going to be equation 3. All right, did everybody get that free body diagram? And now you might have chosen a different direction to be positive, as long as you got a consistent direction to being positive. So for instance, if you saw M2 going down was negative, then that would have made TR positive, that would have made M1G positive, and that would have made TL positive. So if you did that, that's fine too. Now, can someone tell me an equation to relate? Because we've got now TL, TR, those are 2 unknowns. We got A, that's a 3rd unknown. And we got alpha, that's a 4th unknown. So we need 4 equations. Can anybody tell me what the 4th equation is going to be?
A equals R alpha.
Excellent. That's it. Perfect. All right. Do y'all remember what we did to solve this problem when we did it just now?
Plug T and R into the into equation 3.
Exactly. So you're going to take 1 and solve for TR. You're going to take 2 and solve for TL and plug them into equation 3. Y'all want to give that a try? I'm going to do it alongside. You're doing really good.
Yes, sir. Understood. Yes. You calculate time and the instructions within 120. I'll be asked the right to go to down this by stream.
By the way, there's a common factor of R in equation 3. So before you do that, you might want to before you plug TL and TR in that, you might want to cancel out one of the one of the big R's in equation 3. And that looks like this basically. This R and this R could be factored out. And it'd be big R times parentheses TR minus TL. And then that's going to get rid of that and just leave an exponent of 1. So now you can plug that in.
Put her an hour.
So I'm going to go ahead and plug in TR in this new form. Somebody has their voice on. I think it might be Lauren, or Famata, perhaps. Or is that you?
You better
Jamie?
watch where you're going. Oh,
Hey, Lauren, I can hear you.
oh, oh, oh.
Let's see.
Hit the gas, hit the gas, hit the gas.
It's FAMA
Oh, what did they
TTA.
do?
I don't know how to pronounce the name.
Come
I
on, I
don't know
got
what
you.
they're
Thank you. Yeah, I just noticed that one's actually.
What kind of people?
There you go. All right, I got that taken care of. All right, so now I have TR minus TL equals 1/2 M times R times alpha. Anybody know what R times alpha is?
R times alpha is just A.
Exactly. So now all you have to do is you've got A in there. So now I'm going to say TR, which is M2 G minus M2A. I'm separating them again. And then I have minus TL. So I got to remember to distribute that. That's minus M1A minus M1G is equal to 1/2 big M times A. And this will be called equation 5. Say, whoa, stupid thing turning into an eraser. I'm going to call that equation 5. But notice we now have exactly one unknown. We only have the A that's unknown. So on the, that's also supposed to be a 2 over here. Put that 2 back down there. Okay. So I'm going to take and write equation 5 in a more happy way, or a way that's easier for me to fix. So I'm going to say it's M2 minus M1 over, notice when I take the M2A to the right hand side, it's going to be plus. And when I take the M1A to the right hand side, it's going to be plus. So that's going to be 1/2 big M plus M1 plus M2. Each of those are times A, so I'm going to factor out the A. So that gives me M2 plus M1 plus 1/2 M. That's what my denominator is. And of course, when I did M2 minus M1, I'd actually factored out a G. So that's what A is. And notice in this case, if you let big M equal 0, in other words, a massless pulley, then you get again exactly the equation for the normal Atwood machine. Now, if I want alpha, I just divide this by R. So I'm going to actually take, in this case, I'm going to say alpha is equal to M2 minus M1 over M2 plus M1 plus 1/2 big M times G over big R. Because G over big R has units of radians per second squared, so it works out kind of nicely. Okay. Again, if you consider the big M equals 0, you get a formula that looks a lot like just plain A. The only difference is, of course, it's been divided by R to get rid of the units. So we've got A and alpha in here. Now let's look at what TR is going to be. According to this, TR is going to be M2G. So I'm going to say M2 times G minus M2 times A. So in this case, I'm going to say minus and that's going to be M2 squared minus M1 M2 over M2 plus M1 plus 1/2 big M times G. Well, this is clear. I would like to have a common denominator. So I'm going to get a common denominator for that M2, and that common denominator is going to be, of course, the same denominator I have here. So when I multiply M2 times M2, I get M2 squared. That's the M2 in front of the G times the first M2 in the denominator, plus M2 times M1, that'll be M1 M2, plus 1/2 M times M2. So I'm going to say plus 1/2 M2 times M. And I've left out G and all that because we're going to pull out G anyways. But now I have minus M2 squared. That's from the first term in the second fraction. And then plus M1 M2. Okay, all that is in the numerator. And then the denominator is still the same thing, M2 plus M1 plus 1/2 big M. Now, it's kind of hard to see, but what I'm going to do is I'm going to erase that, put that equal sign a little bit closer. And now I'm going to show the G that I factored out. I'm just going to put that in front here. Okay, because it works. So now you can see by doing that little step, the M2s actually cancel out. I got an M2 squared and an M2 squared plus and minus, so that cancels out. But the M1, M2 actually doubles up. So I get ultimately T right is equal to 2M1, M2 plus this weird thing, 1/2 M2 M over M2 plus M1 plus that weird thing, 1/2 M. All that times G, which you could also write as 2M1 plus 1/2 big M over M2 plus M1 plus 1/2 big M times M2G. Then it's like a dimensionless quantity with the units, a number multiplied by it that has the right units. And that's that. So notice if you examine the case of a massless pulley, the big M's being 0 automatically gives you exactly the Atwood machine. So your job, again, extra credit. Solve this methodically and neatly from start to finish. So I've done everything except for solve for TL now. So you've got to now do that and turn that in. It'll be a great exercise for you. That's sort of why I was compelling you to do the stuff alongside me in hopes that you were getting enough experience just from that. But if you take the extra time to do this now, I think you'll get an even better experience. It's actually 6:40. I'm going to do one more problem. That means it's time for you guys to go. You can go ahead and go. I'm just going to explain this quick conservation of energy problem on here. And it'll be on the video and it'll also be on this. So I'm going to go ahead and start that real quick. It's actually pretty simple. What I'm going to do is I'm going to imagine a cylinder again, just because we happen to know what that moment of inertia is. So this is I. This is I equals 1/2 big M R squared, because this is a cylinder of radius big R and mass big M. And it's sitting on an incline. And it's going to roll down. And when it gets to the bottom, I want to know what is V, and I also want to know what is omega. Okay. we don't really need an angle here. What I'm going to do is I'm going to specify that the distance from here to the bottom is big H. So the bottom of the sphere down to the bottom, or bottom of the cylinder, excuse me, down to the bottom of the cylinder when it's in the ground, that's a distance H away. And if you remember, we used conservation of energy. That said work in plus potential energy initial plus kinetic energy initial is equal to work out plus potential energy final plus kinetic energy final plus E loss. So that was my version of the equation because it allowed for a lot more stuff. When I go to fill this in, I'm going to get 0 plus big M G H plus 0 because it's starting at rest. Okay, is equal to 0 plus 0 because we're saying the 0 of height is the level of ground that it ends up on. Plus, now here's the weird part. You have 1/2 big M V squared, and that V is something we want to know. That's the kinetic energy due to the center of mass rolling. But we also have plus 1/2 I omega squared because the object's actually rotating about its center. And that rotation has a kinetic energy associated with it. And the rotational analog of M is I, and the rotational analog of V is W, or excuse me, is omega. So we have that, and it's rolling without slipping. Since it's rolling without slipping, that means V is equal to R omega. So I can actually plug that in, and now I'm going to have big M G H is equal to 1/2 big M V squared plus 1/2 I is going to be 1/2 M R squared. And then omega is equal to V over R. And that's going to be squared. So I'm going to get MGH is equal to 1/2 MV squared plus 1/4 M. Notice the R squared here cancels out with the R squared down here. And I'm just going to get 1/4 MV squared, which gives me 3/4 MV squared, which says now that the masses are irrelevant. And I get, in fact, that V is equal to the square root of 4GH over 3. Okay, so that's how you can do a conservation of energy problem to calculate velocity at the bottom or something like that. You could also do it with dynamics, calculate what the A is. You'd find out that the A is a constant, and then you could just use your kinematic equations to figure out what the velocity at the bottom would be. We also need omega though, and omega is V over R. So what we do is we'd say omega is in fact equal to the square root of 4GH over 3, all that divided by R. So that's like the simplest way to do it. All right, that's it. That's the last type of problem I wanted to make sure you guys had seen. Of course, we're done now. This is really more than enough to get you through all of chapter 11 combined with what I did last time. You'll see I put some more links to videos on our week 12 module, and I put your chapter 11 homework on your week 12 module. So just keep an eye out on your email. Remember, you guys don't have class tomorrow, so enjoy your day off. Go vote. Everybody should vote if you're eligible. Don't break any laws, of course. But have a good one, and I'll see you next time. If you have any questions, I'm going to wait for you in case you have them. Kevin, do you have any questions? All right, it looks like everybody's done.